again to this physics session. I am Dr. Suman Bhatnagar. I am a faculty at Prepaze. So this is the second session on forces. Last class basically we finished up till dynamic and kinetic friction. So from now we'll start in today's session. We'll discuss Newton's laws and we'll see how many if we can do a questions or two in this session. Just before starting, I will like to introduce you to Prepaze. Okay, so Prepaze is basically an online platform. Over here, you can find teachers from all over the world, and there are a lot of experts like me, which can teach you at the comfort of your home. So you can learn from them, understand from them, okay, and clarify all your doubts. All right. So do check the website and book a free trial class. So let's discuss now. Let's begin today's session and continue on with the forces chapter. So we discussed up till the next class the basically different kind of contact forces and the non-contact forces. Okay, today we will discuss Newton's laws of motion. So Newton's laws of motion. Let's discuss them. So Newton's first law of motion, it is also called law of inertia. Newton's first law of motion, it is also called law of inertia. Now, what is it exactly? Is basically that the statement goes up like that. The statement is very important, okay, because it is asked directly as a question. So do write it exact words, okay. It's better you'll get the full marks, okay. It's like that. An object at rest will remain at rest, or an object moving with constant velocity will continue to move with same constant velocity unless acted upon by an resultant unless acted by an unbalanced force. All right, please try to understand the statement. What does it say? It says that's an object at rest. Suppose, let's say, if I take a ball, okay, or any object which is just kept on the surface. This is just kept. Can it move on its own? No, you cannot move it on its own. So it will remain at rest. Or suppose, let's say, an object moving in the constant velocity. Constant velocity, suppose that's the same thing over here. Let's say you have an object and basically it is moving with the same constant velocity v. It is not changing. Can it change its velocity on its own? No, it cannot change its velocity on its own. So for both the cases, when the object is at rest or the object is at moving with the constant velocity, over here, for both of these cases, you require an external force. Only then your state of motion will change. From rest, it will move, and or from moving the constant velocity, it will basically increase or decrease the velocity will happen. Nothing can happen on its own. All right, if there is no external force or unbalanced force acting on the object. So this is the statement of Newton's first law. Why it is called law of inertia? So let's understand that first. What is inertia, first of all? Inertia is basically a property of mass of object. The more the mass of an object, more inertia it will have. So inertia, you can think it of, it is a tendency of the body. It is basically a tendency of a body to remain as it is or does not change its state. Okay, if it is at rest, it wants to stay at rest. If it is moving with a constant velocity, it is moving with a constant velocity. So that basically relates, the first law relates to inertia. That's why it is called law of inertia as well. So one more example I will give you of inertia. Suppose, let's say, very common, like how to understand it practically. Okay, let's say you have two friends, okay, and you want to play, and you go to one of the friend, okay, he denies every time. He says that does not want to play. He just denies every time and he has some work, okay, he says something he will randomly will say that he won't be able to come to play. So that person, it's that friend of yours is showing more inertia, okay, that is more resistance. And to go you to another friend, okay, and you say to him that or him or her that you want to play, he or she quickly comes, so that is have a low of inertia, right? So inertia, you can think it of, it is a tendency of the person to deny everything, or a resistance basically. All right. So the more, it's basically a property of the mass. The more the mass, more will be the inertia. Or let's say, suppose very simple thing. Suppose you have very heavy ball, okay, and you want to move the ball, or you want to kick that ball. Obviously, it is very difficult to move it because the mass is more, its inertia is more. That is, it want to remain at rest. All right. If it is moving at the constant velocity, it will remain at constant velocity because it is quite heavy, and to change its state, you require a lot of force. So that is why you can relate this Newton's first law with inertia. Okay, so hope this idea is clear to you. That's why it's also called law of inertia. Very practical and a example of law of inertia, which is in day-to-day life you must have experienced. Okay, this is a very common example. I don't know if you have heard of that. If you have experienced it, I think it will you have definitely have experienced that. Suppose let's say you are moving in a bus, okay, and the bus or the car, whatever it is, or a metro train, it suddenly stops. What happens? You feel a push basically forward. Why? Because your body tendency was to move with the bus. Your body tendency was to go forward, but the train suddenly stops. That's why you feel that you have a sudden push forward. The opposite thing happens. Suppose let's say the car or the bus you are over there, and the whatever the vehicle you are inside, and it suddenly starts to move. Then you feel a push backwards. Why? Because your body wants to remain at rest. That is a tendency of your body. So that's how basically that's a very common example. We give an application of Newton's first law in the case of a real life. All right, hope that is clear. Let's move to the next law. It is Newton's second law of motion. Newton's second law of motion. Newton's second law of motion. Now that is very important. It's a statement of this goes like this. If there is a net force on an object, okay, I'll just write the statement when there is a resultant force on an object, it will accelerate. The resultant force is directly proportional. The resultant force is directly proportional to the acceleration of the object, to the acceleration of an object, and in the same direction of the acceleration, and in the same direction as the acceleration. That is basically, if you write in a mathematical form, F net is directly proportional to the acceleration. If you remove the proportionality, F net will become equal to ma, that is mass into the acceleration, F net. So whenever there is a resultant force on object, it will accelerate. The resultant force is directly proportional to the acceleration of the object and in the same direction of the acceleration. Wherever there is an acceleration, the net force has to be in the same direction. Now, whatever I say, it might look like it's a normal, what a normal saying which I'm doing, but it's not. It is very conceptual and it is not that easy to understand. When we start doing the questions on this, you require a lot of practice for to be a master of doing questions of Newton's laws based on forces and friction and whatever it is, because depending on the level of your curriculum, your questions can be it easy and can be extremely hard as well. All right, so this will be doing few questions to make you understand what exactly different type of questions can arise. For example, very simple example I can give you on this Newton's is that consider, suppose there is a block. There is a block and there is a force which is acting on this, and there is a friction force which is acting backwards, and there is a normal reaction force above, and there is a basically W weight over here. So this is basically called a free body diagram. Okay, it is basically a free body diagram is that where you draw different forces on an object. Now I'm saying that the object is moving in this direction with an acceleration A. Now, if it is moving in this direction with an acceleration A, that means the vertical forces will be balanced and will be equal to W. And what is F net on the block then? It is equal to F minus F. That is force acting on that forward direction minus the force of friction. And this F net is equals to what? It is equal to M. That is the equation of it. All right. Consider now, if suppose that the block over here is on an inclined plane. Okay, inclined plane, there is basically a different aspect. So let's discuss this a bit later. So because you need different things, a little more understanding of the Newton's laws to do inclined plane problems. Right now, let's focus a bit or more on the smooth plane surface, and we'll go as a class proceed. We'll proceed to the inclined plane problems as well. All right. So this was Newton's second law. I think I hope you must have understood it. The third law, which is the last law which comes in this, is Newton's third law. Let's discuss that. Newton's third law of motion. Now, what's the statement of it? It goes like this: for every action, there is an equal and opposite reaction. Or suppose another word we can say, if a body A exerts a force F on body B, and equal and opposite force is exerted by body B on body. Alright, that is basically if you see the direction FBA, that is the force on B due to A is equals to, I'm writing in the vector form, minus FAB. The magnitude are equal. The magnitude of both these forces are equal, but there is a negative sign which says that the directions are opposite. Alright, so this is called the action and reaction. So this FBA and FAB, these both are called action and reaction pair. Opposite action, reaction pair. Very important point to understand. Okay, in this, I'm saying a body A exerting a force on body B and a body B on body A. There are two bodies involved. Now, if a question, there is a one of the question which is quite popular. Let's say consider a block. We say there is an mg x on the kept on the surface only. There is an mg downwards. There is a normal reaction upwards. All right, we say this thing. Okay. Now the question goes that is N or the normal reaction force, when I did Fn also, is Fn and mg, that is the weight, are action reaction pair. This is N or Fn, basically both are same. I will just write Fn to be more, this is a normal reaction force, so Fn is a normal reaction force, and so I'm asking that Fn and weight W, are these action reaction pair? The answer to this question is no, they are not. Why not? Because they are acting on the same body. Why? Because acting on same body. That is the mass, right? This mass over here. The body is same. That's on both of the forces or on the same body. Whenever we draw a free body diagram, we draw on the single body. Do remember this. We draw, every time we draw the free body diagram, we do it on a single body and not taking a as a system. So these are two, these not are action. What would have been an action pair? Suppose this box is kept on the earth surface. Earth surface, or let's say table. Let's say this box is kept on table. There is a weight of the box. The weight is exerted by the earth on the box. Now, what would have been an action pair? The force with which the box is pulling the earth. Or we can consider the contact surface between the table and the box. So the table is exerting a normal reaction force upwards. What would have been action reaction pair of this Fn? Would have been the force exerted by the box on the table. Okay, so there's a lot of difference in this and it's very conceptual. So that was basically about Newton's third law. In the next session, we'll be discussing questions on this. Now, I think almost this part is over, all of the forces. And the main important point, the main important thing in this is the questions. What different type of questions can be framed and how to solve them. We will discuss a few in the next session to understand it. All right. So hope you have learned something from this session, and I believe that you might check the website of Prepaze and book a free trial class as soon as you can, and hope you will like that. So we'll meet in the next session in the third series of this forces chapter. All right. Until then, okay. See you. Bye. Bye. Take care.